Welcome, everyone, to Lecture 11 of GFE0007, Data Analytics Made Easy for Beginners. Today, we are going to explore a topic that I consider one of the most practically important and intellectually rich areas of the entire course, analytical engineering. Over the past 10 weeks, we have built up a strong toolkit. We have covered probability, classification, regression, clustering, decision trees, ensemble methods, and even text mining. All of that is essential, and I hope you now feel comfortable with those techniques. But today, I want to take a big step back and ask a deeper question. How do we actually apply all of those tools to solve a real business problem? Because here's the truth about professional data science work. Real problems do not arrive pre-labeled and pre-packaged the way they do in textbooks. A business manager does not walk in and say, please run a random forest classifier. They walk in and say, we are losing customers and we do not know why, or we want to increase revenue from our marketing budget. It is your job, as the data scientist, to translate that messy business question into a precise analytical task. And that translation process is what we call analytical engineering. This lecture is going to be rich with conceptual insight and hands-on examples. We have 2 detailed case studies lined up today, and we will be working through mathematical frameworks that will fundamentally change how you approach problem solving. By the end of this lecture, you will think about data science problems in a completely new way. So let us get started. Let me first walk you through our agenda for today. We have 5 major sections structured carefully to build on each other. We will begin with the core of analytical engineering, where we define what this discipline actually is and introduce the expected value framework, which is the mathematical backbone of almost every engineering solution we will discuss. Then we will move into our first detailed case study, the charity mailing problem. This is a beautifully constructed example that demonstrates the power of the expected value approach, and it will also reveal some important pitfalls around data quality that you need to know about. After that, we will tackle our second case study, sophisticated churn management. This is a multi-level example where we will see how analytical thinking can evolve from a naive approach to a genuinely sophisticated causal framework. Then we will cover strategic implementation, how you actually manage analytical engineering projects in the real world. And we will wrap up with a summary and principles section that distills everything into 4 key takeaways you can carry forward. Each section builds on the last, so I encourage you to follow along carefully. There will be mathematical equations, and I will explain every single one of them in plain English. Ready? Let us go. Section 1, the core of analytical engineering. I want to start with a very honest observation about what it is really like to do data science in a business setting. Most academic courses, including the first 10 weeks of this course, teach you algorithms. We teach you classification. We teach you regression. We teach you clustering. These are extremely valuable, but they represent only one part of the actual job. In the business world, problems are rarely, if ever, pre-packaged. When you start your career, you are not going to receive a clean data set with labeled examples and a clear objective function. You are going to receive ambiguous, messy problems. And the gap between here is a messy business problem and here is a trained model that solves it is enormous. That gap is what analytical engineering fills. Think about it this way. Stakeholders, your managers, your clients, the executives who fund data science projects, they do not ask for a random forest model. They ask you to reduce churn. They ask you to increase revenue from the marketing budget. They ask you to improve customer satisfaction scores. These are goals, not algorithms. Your job is to design the path from goal to solution. That design work, which combines domain knowledge, business logic, statistical thinking, and technical execution, is what we mean by analytical engineering. I want you to think of it as a bridge. On one side of the bridge, you have a business problem expressed in business language. On the other side, you have a data science solution expressed in mathematical and technical language. Analytical engineering is the art and science of building that bridge. And it is a skill that is genuinely rare, genuinely valued, and genuinely separates excellent data scientists from average ones. Now let me give you a precise definition to anchor everything we are about to do. Analytical engineering involves designing an analytical solution based on the data, tools, and techniques available. That is the formal definition. But let me unpack it, because there is a lot inside those words. First, notice the word designing. Engineering is not just computing, it is designing. You are making choices about how to decompose a problem, which data to use, what assumptions to make, what to simplify. Every engineering decision has trade-offs, and good engineers navigate those trade-offs consciously and transparently. Second, notice the phrase based on the data, tools, and techniques available. This is critical. Analytical engineering is not about building the theoretically perfect solution. It is about building the best solution you can actually build, given real-world constraints. You might not have the ideal data. You might have budget or time constraints. You might be limited to tools your organization already owns. Good analytical engineers work within these constraints creatively. Now, there are two core mental processes at the heart of analytical engineering. The first is decomposition. This means breaking a large, messy, complex business problem into smaller, more solvable subtasks. Problems that feel overwhelming and intractable become manageable when you decompose them thoughtfully. The second process is recomposition. Once you have solved the individual subtasks, perhaps you have trained several separate models, each addressing one piece of the puzzle, you need to put those results back together in a way that actually answers the original business question. The subtask results must be recomposed into a final business decision or recommendation. Decomposition breaks the problem apart. Recomposition puts it back together. These two processes, working together, are the essence of analytical engineering. Keep them in mind throughout everything we cover today. Now I want to introduce what I consider the single most powerful tool in the analytical engineer's toolkit, the expected value framework. Once you understand this framework, you will find yourself applying it to almost every business problem you encounter. It is that broadly applicable. Expected value, which we abbreviate as EV, is a concept from probability theory that you may have encountered before. But in the context of data science, it takes on a special power. Why? Because it forces you simultaneously to think about two things that must both be present for a good business decision: probabilities and business values. Let me explain what I mean by that. A probability is something the data can tell us. Given a customer's profile, what is the probability they will buy? Given a patient's test results, what is the probability they have this disease? We use data and models to estimate probabilities. A business value is something the organization knows. If a customer buys, how much revenue does that generate? If a patient is treated correctly, what is the reduction in healthcare costs? Business values are not in the data. They come from the domain experts and the financial analysts. The expected value formula ties these two worlds together. Let me write it out for you now. The general structure of expected value is EV equals P of O1 times V of O1 plus P of O2 times V of O2, and so on for all possible outcomes. Let me read that carefully in words. For each possible outcome, let us say outcome 1, outcome 2, and so on, we multiply two things. First, the probability that this outcome occurs, which we write as P of O sub I, and second, the business value of that outcome, which we write as V of O sub I. We then add up all of these probability times value products across all possible outcomes. That sum is the expected value. This decomposition is profound. It separates the problem into two clean pieces. The probabilities are estimated from data using the statistical and machine learning tools we have been studying all semester. The values come from the business, from accounting records, from pricing models, from strategic decisions. This separation is what makes the expected value framework so powerful and so practically useful. Data scientists contribute the probabilities, domain experts contribute the values, and the expected value formula is the rigorous mechanism that combines them into a coherent decision framework. We are going to see this framework in action through two detailed case studies. The first one is coming right now. Section 2, Case Study 1, the charity mailing problem. Let us meet our first problem. Imagine you are a data scientist working for a charitable organization. This charity raises money by mailing solicitation letters to potential donors. These letters ask for contributions to fund a cause, and some percentage of recipients actually donate. Now here's the business constraint. Mailing is not free. Every letter costs money. It costs money to print it, costs money to stuff it in an envelope, and costs money to pay for postage. All of that taken together, let us say each mailing has a cost, which we will call circa. So whenever the charity sends out a letter, they are making an investment. They are spending money C in the hope of receiving a donation in return. Now, what is the naive approach to this problem? The naive goal would be to maximize the number of donors. In other words, send the letter to everyone who has a high probability of donating. If someone seems likely to give, send them a letter. That sounds reasonable on the surface. But let me show you why it is wrong. The naive goal of maximizing donors is the wrong goal. The correct business goal is to maximize total donation profit. Profit means revenue minus cost. The revenue is the donation. The cost is the mailing expense. These two things must both be in the picture. If you ignore the cost, you will make poor decisions. Your job as an analytical engineer is to ensure that your model and your decision rule are aligned with the actual business objective, which is profit, not volume. This distinction between the naive goal and the business goal is subtle but absolutely crucial. It is exactly the kind of thing that separates a data scientist who adds real value from one who technically produces a model but ends up misleading the organization. Let us see how the expected value framework helps us get this right. To make this concrete, let me give you a simple but powerful numerical example with two fictional potential donors. I want you to think carefully about this because it perfectly illustrates why the naive approach fails. Donor A has a 90% chance of donating. 90% is a very high probability. If you are running a simple classifier that predicts will donate or will not donate, donor A is almost certainly labeled as a will donate. Your model would target this person, and it would feel like the right call. Donor B has only a 5% chance of donating. 5% is quite low. The same classifier would almost certainly label donor B as will not donate and would not target them. But now let me add the critical piece of information that the simple classifier is ignoring. Donor A, if they donate, gives exactly $1. Donor B, if they donate, gives $100. Let us now compute the expected value of targeting each of these donors, given that the mailing cost is $2. For donor A, the expected donation is 90% times $1, which is 90 cents, but the mailing costs $2. So the expected profit from targeting donor A is 90 cents minus $2, which equals negative $1.10. Targeting donor A is a guaranteed expected loss. For donor B, the expected donation is 5% times $100, which is $5. The mailing costs $2. So the expected profit from targeting donor B is $5 minus $2, which equals positive $3. Targeting donor B is a profitable decision. So the naive model, which ranked donor A as a high priority target and donor B as a low priority target, has it exactly backwards. By ignoring donation amount, the naive model would have the charities spend money in ways that generate losses and miss opportunities that generate profit. This is why probability to donate alone is insufficient. We need to predict value, not just probability. The expected value framework gives us the tools to do. Now, given the expected value formula we just derived, we can state a very precise decision rule. We should target a prospect if, and only if, the expected value of targeting them is greater than 0. In other words, we should send a mailing to a prospect only when the expected profit from doing so is positive. This is the decision rule in its simplest, most elegant form. Mail to a prospect if and only if their probability of responding, multiplied by their expected donation amount, exceeds the cost of the mailing. In other words, the expected donation revenue must exceed the mailing cost. This decision rule is perfectly and precisely aligned with the business goal of maximizing profit. Every prospect for whom this inequality holds is worth targeting. Every prospect for whom it does not hold should not be targeted. The model is not just a classifier that predicts behavior. It is a profit optimization tool. This is the power of designing a solution from first principles using the expected value framework. We have just engineered a beautifully structured solution, but I now want to warn you about a critical implementation challenge that can undermine even the most elegant model design. This challenge is called selection bias, and it is one of the most important practical issues in applied data science. Recall that to build our donation amount model, the model that estimates V sub R of X, the expected donation given response, we need historical data on donation amounts. Specifically, we need data on how much past donors actually gave. Where do we get that data? We look at our historical records. Here is the catch. Our historical donation records only contain data for people who actually donated in the past. People who received a mailing but did not donate are not in the historical donation dataset because there is no donation to record. So when we train our donation amount model, we are training it exclusively on a subset of the population that already chose to donate. These people who chose to donate in the past are very likely to be systematically different from the general population we want to target now. Think about who tends to donate to a charity. They are probably older on average, more philanthropically oriented, more financially established. They share characteristics that made them donors in the first place. If we train a model on only these past donors and then use it to predict donation amounts for the general population, we may be making predictions based on a sample that is not representative of the people we are now targeting. This is selection bias. Our training sample was selected in a non-random way, and that selection process is related to the very outcome we are trying to predict. The bias it introduces can be severe. Predictions from a biased sample can be badly miscalibrated when applied to the broader population. This is a critical engineering hurdle. Recognizing it, quantifying its potential impact, and finding strategies to mitigate it, such as collecting more representative data or using statistical correction techniques, is part of what a skilled analytical engineer does. The mathematics alone are not enough. You also need to think carefully about the data generating process behind your training data. Section 3. Case Study 2. Sophisticated Churn Management. Our second case study is one of the most important practical problems in any business with recurring customers: churn management. Churn refers to customers canceling their subscription or service and leaving for a competitor. This is a problem faced by telecommunications companies, streaming platforms, banks, software companies, and any other business that depends on retaining existing customers. I am going to walk you through 3 levels of thinking about this problem. Each level is more sophisticated than the last. The purpose is to show you how analytical engineering evolves as your thinking deepens. Level 1 thinking is what most people naturally do when they first approach a churn problem. The question they ask is, who is most likely to leave? To answer this, they build a binary classification model that predicts churn versus stay for each customer. The model takes in customer features, usage patterns, billing history, customer service interactions, contract length, and outputs a churn probability. Customers with high churn probability are flagged for intervention, perhaps a retention offer, or a phone call from the customer service team. This approach is logical and it has intuitive appeal, but it has 2 significant problems that are easy to miss. The first problem: the model might identify customers who are indeed going to leave, but who are going to leave no matter what you do. No retention offer will save them. Perhaps they are moving abroad, or they found a competitor offering something your company simply cannot match. These are the lost causes, and targeting them with retention offers wastes resources. The second problem: the model might prioritize high churn probability customers who have very low value to the business. Perhaps they are small accounts, minimal revenue, not worth significant retention spending. Meanwhile, low probability churn customers with very high value. Your best customers, your most profitable accounts, might be at modest but non-trivial risk that a simple classifier deprioritizes. So level 1 thinking, while a reasonable starting point, has these fundamental blind spots. Level 2 thinking addresses the second limitation of level 1 by incorporating business value. The question at level 2 is, where are we losing the most money? Instead of just asking who is likely to leave, we now ask how much revenue are we at risk of losing from each customer. The model at level 2 computes an expected loss metric for each customer, which is the churn probability multiplied by the customer value. We write this as expected loss equals P of churn times customer value. This is already an improvement. A customer with a 20% churn probability and a monthly value of $1,000 has an expected loss of $200 per month. A customer with a 50% churn probability and a monthly value of $50 has an expected loss of only $25 per month. Level 2 thinking correctly focuses retention resources on the first customer rather than the second. This is a meaningful advancement over level 1. We are now explicitly incorporating the financial stakes into our prioritization. We are no longer just chasing the customers most likely to leave. We are targeting the customers whose departure would hurt us the most. But level 2 thinking still has a critical blind spot. It tells us who we are at risk of losing and how much that loss would hurt. What it does not tell us is whether our intervention, the retention offer, the discount, the upgrade actually changes the customer's behavior. We are spending resources on retention without any estimate of whether those resources are actually working. Imagine spending $50 on a retention offer for a customer who had already decided to stay, or for a customer who will leave no matter what you offer. You have spent the $50 with zero impact on the outcome. This is the gap that level 3 thinking addresses. Slide 12, level 3 thinking, the causal effect. Level 3 thinking is where analytical engineering reaches its full sophistication. The question we now ask is not just who is likely to churn, and not just how valuable are they, but for which customers will our retention offer actually make a difference? This is a causal question. We are asking about the causal effect of our intervention on the customer's behavior. And this is what makes it so much harder and so much more valuable than level 1 and level 2 thinking. To answer this question, we define a metric called the value of targeting, which we write as V sub T. This is the net business benefit of contacting a specific customer with our retention offer, compared to not contacting them at all. The formula for V sub T is V sub T equals EV sub targeted minus EV sub not targeted. In words, the value of targeting a customer is the expected value we receive if we target them, minus the expected value we would receive if we do not target them. The difference between these two expected values is what our intervention is worth. If this difference is large and positive, the intervention is highly effective. If the difference is small or negative, the intervention is wasteful or even counterproductive. This is the highest level of analytical engineering. We are not just predicting outcomes. We are measuring the incremental impact of a business action. We are asking the counterfactual question, what would have happened without our intervention? And then we are comparing that counterfactual to what happens with our intervention. Let us now look at the 4 distinct types of customers that emerge from this framework. When we contact a customer with a retention offer, one of 4 things can happen, depending on what type of customer they are. These 4 categories form what we call the 4 quadrants of influence, and understanding them is absolutely essential for level 3 thinking. The first category is the persuadables. These are the customers who will stay if we contact them, but will leave if we do not. These are exactly the people we want to target. For persuadables, our intervention genuinely changes the outcome. Their V sub T is positive and potentially large. Targeting them is valuable. These are the golden targets of any retention campaign. The second category is the sure things. These are customers who will stay regardless of whether we contact them or not. They are already committed to staying. If we contact them with a retention offer, we spend the cost of the offer but achieve nothing, because they would have stayed anyway. Their V sub T is negative. We incur the cost of contact with no incremental benefit. Targeting these customers wastes money. The third category is the lost causes. These are customers who will leave regardless of what we do. No offer is compelling enough to retain them. Perhaps they have already made up their mind to switch, or the reason they are leaving has nothing to do with anything we can address. If we target them, we spend the cost of the offer and achieve nothing. Their V sub T is also negative. Targeting these customers also wastes money. The fourth category is perhaps the most counterintuitive, and it is one of the most important insights in all of marketing analytics. These are the sleeping dogs. These are customers who will stay if we leave them alone, but who will actually leave because we contacted them. How is this possible? Think about it. Sometimes a marketing contact reminds a customer of something they were subconsciously dissatisfied with. Maybe the retention call forces them to reflect on their subscription costs, and they realize they are paying for something they barely use. Maybe the promotional offer we make them actually signals that a better deal is available, and they start shopping around. Whatever the mechanism, the intervention causes harm rather than good. For sleeping dogs, their V sub T is negative, because contacting them makes the situation worse. So of the 4 types of customers, only one type, the persuadables, is worth targeting. Level 1 and Level 2 thinking cannot distinguish between these 4 types. Level 3 thinking, through the value of targeting framework, is designed precisely to identify the persuadables and target only them. Now let us do the full mathematical decomposition of the value of targeting formula. This is the centerpiece of the Level 3 analysis, and I want you to see every piece of it clearly. We expand the V sub T equation. The result is V sub T equals the quantity P of S given X comma T minus P of S given X comma not T times U sub S of X minus C. Let me walk through each component carefully. P of S given X comma T is the probability that the customer stays, given their feature profile X, and given that we do target them with our offer. This is what happens with the intervention. P of S given X comma not T is the probability that the customer stays, given their feature profile X, but given that we do not target them. This is the counterfactual. What would have happened without the intervention? The difference between these 2 probabilities, P of S given X comma T minus P of S given X comma not T, is the causal effect of the intervention on the probability of staying. For persuadables, this difference is positive and large. For sure things and lost causes, this difference is near 0. For sleeping dogs, this difference is negative. U sub S of X is the business value of the customer if they stay, essentially the customer's lifetime value or ongoing revenue contribution. and C is the cost of the retention offer. So the three subtasks of Level 3 analytical engineering are: first, estimate the probability of staying if targeted, which requires data on customers who received an offer. Second, estimate the probability of staying if not targeted, which requires data on customers who did not receive an offer. And third, estimate the customer value if they stay, which comes from financial records. Once we have all three of these subtasks solved, the V sub T formula recomposes them into a single targeting decision. Target a customer if and only if their V sub T is positive. This is precise, this is principled, and this is aligned with the true business objective. Now you might be thinking, this Level 3 framework sounds incredibly powerful, but it also sounds incredibly demanding in terms of the data required. And you would be right. There is a very common practical challenge that arises when trying to implement this approach, and I call it the data gap challenge. The core difficulty is this: to estimate P of S given X comma T, the probability that a customer stays when targeted, we need historical data from customers who received our retention offer and either stayed or churned as a result. But what if the offer is new? What if this is the first time we have ever run this type of retention campaign? There is no historical data yet, because the offer has never existed before. We are in a chicken and egg situation. As an analytical engineer, you have two main strategies for dealing with this data gap. The first strategy is to use a proxy label. This means finding a related, older data set that is similar enough to stand in for the data you do not have. Perhaps your company ran a different retention offer 2 years ago, a different discount, or a different product upgrade, and you have historical data from that campaign. If the customer behavior in response to that old offer is likely to be similar to their behavior in response to the new offer, you can use that old data as an imperfect but usable proxy. You should always be transparent about this approximation and acknowledge its limitations. The second strategy is to invest in data by running a randomized pilot study. Before the full campaign launch, deliberately contact a small, randomly selected subset of customers with the new offer and leave another randomly selected subset uncontacted. Because both groups were randomly selected, any difference in churn rates between the two groups can be attributed to the offer itself. This is causal identification. The pilot gives you the data you need to estimate P of S given X comma T, and this data can then be used to build the full model for the large-scale campaign. Both strategies require judgment. Proxy labels are quick but approximate. Pilot studies are precise but costly and time-consuming. The choice between them depends on the scale of the campaign, the stakes involved, and the budget available. This kind of judgment call is exactly what analytical engineering demands. Section 4, Strategic Implementation. The data gap challenge from the previous slide leads us into a broader and very important strategic idea. Data is not just an input to analysis. Data is a strategic asset that should be actively invested in and grown over time. In most organizations, data is treated passively. It is collected as a byproduct of operations, and then analysts use whatever happens to be available. But this passive approach has severe limitations, as we just saw with the data gap challenge. The best data scientists and the best organizations think about data proactively. They ask, what data do we wish we had? What data would make our models dramatically better? And how can we design our operations to collect that data? I want to give you a remarkable real-world example of this strategic thinking at its best. It involves Signet Bank, which you may know today as Capital One. In the 1990s, the credit card industry was highly standardized. Every bank essentially offered the same products at similar interest rates, because none of them had the data or analytical capability to differentiate. Signet Bank's analytical team realized something extraordinary. If they could collect the right data, they could predict credit risk much more accurately than their competitors, and this would give them a massive competitive advantage. To collect that data, Signet deliberately extended credit to some high-risk customers that other banks refused. Yes, they took losses on some of these customers, but in doing so, they observed how these high-risk customers actually behaved. How many defaulted, under what circumstances, and what features predicted default most reliably. This data was enormously valuable. It gave them a picture of credit risk that no competitor had. They used that data to build much more accurate risk models, which allowed them to price credit more precisely, expand into underserved markets profitably, and ultimately build what became Capital One, one of the world's most successful data-driven financial companies. The lesson here is profound. Sometimes the best investment you can make is not in marketing or operations or product development, It is in data. Deliberately designing situations to collect the data you need, even at short-term cost, can generate enormous long-term analytical advantage. This is strategic data investment, and it is a core part of analytical engineering at the highest level. Let me now talk about something that is rarely covered in data analytics courses, but is critically important in practice: how to actually manage the analytical engineering process over time. The first and most important thing to understand is that analytical engineering is iterative. It does not work like a waterfall process where you define the problem once, build a model, deploy it, and you are done. Real-world analytical engineering is a continuous cycle of refinement. As you start working with the data, you discover things you did not know at the outset. You discover that a feature you thought would be important is actually unavailable. You discover that the business process generates data with systematic biases you had not anticipated. You discover that the definition of churn used by the business team is subtly different from what the data records. As these discoveries accumulate, you must go back and refine the problem formulation. Sometimes what you discover in the data reveals that the business problem was not precisely defined in the first place. A good analytical engineer does not just power through with the original formulation. They loop back, have the conversation with the business, update the formulation, and restart the modeling process with a better defined objective. This brings me to the second critical point. Communication between data scientists and business managers must be continuous. This is not a one-time handover. The problem can and does drift over time. The business context changes. The data changes. Regulatory environments change. Customer behavior changes. Any of these shifts can invalidate assumptions that were reasonable at the start of the project. If data scientists disappear into a technical bubble for 3 months and then emerge with a model, only to find that the business problem has fundamentally changed in the meantime, the entire effort may be wasted. Frequent, short feedback loops between the analytical team and the business stakeholders are not just nice to have. They are essential to ensure that the work being done remains aligned with the actual business need. Build regular checkpoints into your project plan. Share preliminary results early. Invite feedback. Adjust accordingly. The third major dimension of practical analytical engineering is knowing when and how to make simplifying assumptions. And this is a genuine skill that develops with experience. Here is a truth that every practicing data scientist must accept. You cannot model everything. Every real-world problem has more complexity, more nuance, and more potential interactions than any model can fully capture. There will always be factors you cannot measure, dependencies you cannot quantify, and edge cases you cannot handle. The question is not how to achieve perfection. The question is how to achieve a solution that is good enough to be useful, within the constraints of your data, your budget, and your time. Good analytical engineers know when to stop. They recognize 3 specific stopping conditions that justify a simplifying assumption. The first is, we cannot get data on this event. If a factor is important in theory but unmeasurable in practice, you have to proceed without it. Document the assumption. Estimate the potential impact of the missing factor, and move on. The second is, modeling this detail is too expensive. Sometimes the incremental improvement from modeling a particular feature or interaction is real but small, and achieving it would require a disproportionate investment in data collection or computational resources. Good engineers make a judgment call. Is the improvement worth the cost? Often the answer is no. The third is, this assumption is good enough for now. In iterative analytical engineering, you do not need a perfect model before you deploy something. You need a model that is better than the current baseline. You can start with a simplified version, measure its performance in practice, and incrementally improve it over time based on real feedback. This iterative improvement approach is far more effective than trying to build the perfect model before deploying anything. The art of making good simplifying assumptions separates effective engineers from those who get stuck in analysis paralysis. Know when good enough actually is good enough, and have the professional confidence to say so clearly. Section 5. Summary and Principles. We are coming to the end of today's lecture, and I want to distill everything we have covered into 4 core principles of analytical engineering. These 4 principles are a framework you can apply to virtually any data science problem you encounter in your career. Principle number 1. Decompose. Always start by moving from the business problem, expressed in business language, to specific, manageable data science tasks. Break the problem into subtasks. Ask what probabilities need to be estimated, what values need to be quantified, and what data is needed for each. A problem that feels overwhelming becomes tractable when it is broken into its component parts. Principle number 2, expected value. Once you have your subtasks solved, use the expected value framework to reassemble them into a coherent business decision. This framework ensures that your model is aligned with the actual business objective, not just a statistical proxy for it. It forces you to integrate both the probabilistic outputs of your models and the financial inputs from the business, producing a decision rule that directly optimizes what matters. Principle number 3, causal thinking. Always ask, what is the effect of the intervention? This is level 3 thinking. Do not just predict outcomes, estimate the counterfactual. What would have happened without the intervention? The incremental impact of the action is what you are truly trying to measure. The 4 quadrants of influence, persuadables, sure things, lost causes, and sleeping dogs, are a framework for understanding causal heterogeneity across customers. Principle number 4, invest. View data acquisition as a strategic choice, not just a passive activity. Identify data gaps that limit your analytical capability. Design processes to fill those gaps. Sometimes the best analytical investment is not a better model. It is a better data set. As the Signet Bank example shows, deliberately investing in data can create competitive advantages that last for decades. These 4 principles, decompose, expected value, causal thinking, invest, are your analytical engineering compass. Learn them well. Let me close today's lecture with the big picture message that I most want you to carry forward. Data science is more than algorithms. I want you to remember this statement. When you graduate from this course and enter the workforce, you will be surrounded by colleagues who are excellent at running algorithms. They know how to tune a gradient boosting model. They know how to apply cross-validation. They know how to interpret a confusion matrix. These are valuable skills, and you should have them too. But the professionals who truly stand out, the data scientists who get promoted, who lead teams, who drive real business impact, are the ones who think like analytical engineers. They are the ones who can take a messy, ambiguous business problem and transform it into a precise, well-designed analytical solution. They understand that data science is a design discipline, not just a computation discipline. Analytical engineering transforms data into useful knowledge, not just information. Useful knowledge that drives decisions and creates value. And by using frameworks like expected value and causal thinking, we ensure that our science genuinely solves business problems, rather than producing technically impressive outputs that sit on a shelf and change nothing. I am very proud of how far you have come in this course. You started as beginners, and you now have a toolkit and a mindset that will serve you well in whatever analytical career you pursue. This has been Lecture 11 of GFE0007. Thank you for your attention, and I will see you in the next lecture.